Many thanks to Kadina and Mircea for organising the summer school. I think it's a rather nice idea. It brings together people from different areas under a common theme. I'm going to be speaking about a rather specific subject that they asked me to speak about. It's not a particularly new piece of work. It's about 30 years old, but I think it may be quite appropriate for summer school because it'll give me a chance to discuss a couple of things which are perhaps a little bit difficult for people to notice or recognize when they start out in research, and perhaps it's useful to see someone talk about them. So the topic is sphere packing, and this is one of the oldest problems in what you might call modern mathematics. It goes back at least to Kepler, so it's not as old as squaring the circle, but it's a very old problem in modern mathematics. And the idea is how best can you pack solid spheres in space. And in 2 dimensions, the solution is very simple, both in the sense that it's obvious what you should do, and in the sense that even proving it is also quite straightforward. You can prove it locally. You can look at what happens in a small neighborhood, a small region. How efficiently can you cover, let's say, a hexagonal tile, for example, and then extend that to the rest of space. And so you don't have to worry about looking at huge numbers of spheres or disks all at once. Now, in higher dimensions, it's much harder to determine the maximum. It became a very famous problem even in 3 dimensions. And what I'm going to be talking about mainly is the restriction to so-called lattice packings. So a lattice, well, in the plane, it's a set like this. You have a pair of vectors, u and v, and they're linearly independent. They span the space. And you look at all integer combinations of these, so linear combinations with integer coefficients, and that gives you this very regular arrangement of points in space. And the idea is that you're going to put you're going to center a sphere, or in this case a disk in 2 dimensions, at each point. So just as in this picture you see here is this lattice, and there's a disk whose center is at each of these points. In higher dimensions, we do essentially the same thing. We take a basis, and then we look at all the linear combinations of the basis vectors with integer coefficients. But for the purposes of what I'm doing, it's actually going to be slightly simpler to think of it this way. You take an invertible matrix A, and then you apply it to the usual lattice of integer points. So all of the points of a grid that you would see on graph paper, for example, and you simply apply the linear map to all of those, and that will give you this lattice. So that'll give you the same thing as this. If you like, these vectors here are the columns of the matrix A, something like that. And then, as I say, we now put a sphere of a certain radius, let's say little r, at each of these lattice points. And the hope is, or the plan is, that the interiors of these spheres don't overlap. In other words, any 2 of these lattice points are at least distanced 2r apart, and that means that the balls of radius r at those centered at those respective points will not overlap, except on the boundary, except that they may touch on the boundary, but not their interiors. Okay, so that's our task. Now, lattice packings are very restricted, of course, and so in spirit or in principle, you might expect that it's able to pack. It's possible to pack more efficiently with some other sort of packing, some sort of random-like packing, and therefore to prove better lower bounds on the optimal density with non-lattice packings, to show that there are packings which are better than you can show for lattice packings, but to prove better upper bounds on the density of lattice packings because they're so restricted. In practice, the opposite is true, and actually this is the sort of thing that can happen quite often in mathematics, this sort of counterintuitive phenomenon, that the best upper estimates work for arbitrary packings, while the best lower estimates come from constructions using lattice packings. In other words, the point is that it's hard to construct packings, and having a lattice packing actually gives you some help in constructing it, in describing it, because instead of having to describe billions and billions of the positions of billions and billions of spheres, you just write down your lattice and check that the different points of the lattice are far apart. While in the other direction, although in principle lattice packings should give you some information which enables you to estimate how dense they can be, it's actually very difficult to use the fact that you have a lattice to get an upper bound. It's much easier, in fact, to prove an upper bound that works in complete generality. We don't know how to use the fact that we have a lattice. So you have this rather strange situation that things work the opposite way from what formally you would expect them to, or in a sense logically you would expect them to. Now, what I'm going to do in this talk is describe a particular construction of lattice packings in each dimension, and use that to get a bound on the optimal density from below. So I'm going to prove a lower bound. But before I do that, let me give you the history. So the first sort of reasonably memorable result was proved by Minkowski, who showed that you can pack with density 2 to the 1 minus n. In fact, a little bit more than that, but let's say 2 to the 1 minus n. Asymptotically, that's the right bound. This was improved to a constant times n, times 2 to the minus n by Rogers, and then Davenport and Rogers improved the constant a little bit from 0.6 to 1.68. And their record actually lasted quite a while. And the result I'm going to tell you about, something I proved in 1992, improves the constant a little bit further. So you see this n minus 1 is basically the same as n, but there's a different constant here. It's a 2 instead of 1.68. So that's what I'm going to talk about. Now, this record has been broken since then in 2011 by Stephanie Vance, who got 6 over E instead of 2 there, in case the dimension is divisible by 4. And then following that, Venkatesh got an improvement which goes to infinity with n, but for some rare dimensions. So you need very special number theoretic properties of this n to pick up this log n using an extension of Vance's idea. So that's really the history of the lower bounds. And as I say, this is the one I'm going to discuss here. So it's not the best that we know, but I think, as I say, it's kind of appropriate in a way for a summer school. It's quite an instructive thing to look at. The upper bounds, well, there's an obvious upper bound. You can't have density bigger than 1. You can't cover more of space than there is. The most famous sort of classical upper bound, which improves on this, is by Blichfeld, who got 1 over root 2 to the n. So notice there's an exponential gap here between 2 to the minus n from below and 2 to the minus n over 2 from above. 1 over root 2, or 0.707 to the n from above. This was improved by Kapuscinski and Levenstein, and they essentially hold the record. It's about 0.66 to the n. This is not exactly that, of course, it's something else. There has been a constant improvement of this due to Cohn and Zhao, using essentially the same argument. They sort of tinkered with it a bit and managed to get a constant improvement. But as I say, this is still exponentially larger than the lower bound. So it's 0.66 to the n instead of 0.5 to the n. There's an exponential gap. Now, in specific dimensions, there are some rather famous results. In 1998, Hales solved what was known as the Kepler problem by proving that the best packing in 3 dimensions is the usual packing that you see, packing of oranges in supermarkets or grocers' shops. And this is a very complicated proof using, which is computer aided, and it has been checked in considerable detail, and I think it's now pretty certain that it is correct, although I'm not sure any one person, other than Hales himself perhaps, really feels 100% certain that they themselves have gone through the whole proof, but I think the community now agrees that this is definitely correct. In 2016, Vyazovska got the exact solution in 8 dimensions, and this is a very different kind of result. This is in a sense more like the result in 2 dimensions, except much more difficult, because you have an absolutely perfect packing, and that perfect packing was known for a long time. What was not known was how to show that it was actually the best, how to get some sort of test function which would enable you to prove that it was the best. And Vyazovska, what she did was discover exactly the right test function based on modular forms, and really, I mean, it came completely out of the blue. No one really had any inkling that it existed, but because she worked in modular forms, she somehow realized that it existed, and so actually her proof is in a sense more like the proof of the lower bounds in the sense that it consists of finding an exact sort of perfect object. In this case, not the packing is already known, but the test function which enables you to prove that the packing does a good job. And then she and some collaborators then got a similar kind of result in 24 dimensions. So in these special dimensions, there are these wonderful packings, and it turns out that there are also wonderful methods to prove that they are the best. Now, as I said, I'm going to prove this lower bound in general in n-dimensional spheres can be packed with this density. I've said here 1994, that was when the paper was published. Earlier in the slides, I wrote 1992. That was the time I actually did the work, but it was published eventually in 94. And what I'm going to do, therefore, is construct, in inverted commas, a packing, and it's going to be a lattice packing. That's what I'm going to demonstrate. Now, before I do that, let me slightly reformulate the problem. So we've said that this lattice, so the image of the standard integer lattice by an invertible matrix A, will pack spheres of radius r if the sphere of radius 2r, centered at 0, contains no lattice point in its interior, except, of course, 0 itself. The reason is that because of the uniformity of the lattice, if 0 is at least distance 2r from all the other lattice points, then any pair of lattice points will be at least distance 2r from one another, because you can just translate the whole picture. Translate one of them to 0, if you like. So this is another way to formulate this statement that every pair of lattice points are at distance 2r apart, and therefore that spheres of radius r can be packed by putting one centered at each lattice point. Okay, so this is another way to formulate it, and what we want to do is determine the density of the packing, given that we found this radius r, which can be packed, by finding a ball of radius 2r, which has this property that it sort of fits snugly in, and only one point is in its interior. Only one lattice point is in its interior. So what is the proportion of space covered by this packing? Well, to each lattice point, there is a sphere. So each lattice point has a sphere centered there, and they're the things whose volume we're trying to estimate relative to the volume of space. But at the same time, to each lattice point, there is also a parallelepiped, a kind of a tile, the image of a cube under this matrix A. And these tiles are indeed tiles. They tile the space, so you can break the space up into these parallelepipeds, one for each lattice point. And so what you want is to calculate the ratio of the ball to the ratio of the parallelepiped. You can look inside a parallelepiped, look at pieces, how much of that is covered by these solid spheres. And you can reassemble those into a single sphere, because there's one for each lattice point. So here I've drawn this reassembly of these pieces of this parallelepiped into a single sphere. So the aim is to calculate the ratio of the volume of this ball to the volume of the parallelepiped. Well, the ball is the ball of radius r, so for the moment I'm just leaving that as the volume of the ball of radius r. But I know that in terms of the matrix A, I can calculate the volume of this parallelepiped as the determinant of A. That's exactly the idea that the determinant of a matrix tells you the local volume scale factor that the linear map achieves. So what we want, the density of the packing, the proportion of space covered by these balls, these solid spheres, is the volume of each one divided by the determinant of A, the matrix which is creating our lattice from the integer lattice. Okay, so this is the ratio we're trying to show is quite large, and remember the aim is to show that it's at least this thing here in n dimensions. Okay, so here we are. We want to find a lattice with all non-zero lattice points of length 2r with the property that this is at least this ratio here. Now, instead of doing that, and this is something absolutely standard, which was a method used over and over again. Davenport and Rogers used it. It's a very, very obvious thing to do. That there's a generalization of Minkowski's result called the Minkowski-Klafka theorem, in which the same thing happens. So instead of doing this, I'm going to apply the inverse matrix, A inverse, to the whole picture, as it were. And so I'm going to work directly with the ordinary integer lattice. Here it is. But now you see the aim will be to find not a ball, which contains no point in its interior, no lattice point in its interior other than the origin, but to find an ellipsoid, the image of the ball of radius 2r, under this inverse matrix. So if we can find an ellipsoid, and it has this property that the only lattice point, integer lattice point in its interior is the origin, then we'll have a picture which we could, as it were, transform back into this one, the one that we actually care about, or perhaps this one really here. Yeah. Okay, so this is now the new setup, and as I say, it's a standard way of reformulating the problem that many people used. So let's actually encapsulate what the problem is. We're looking for an ellipsoid, so that's a linear image of the ball centered at 0. It should contain no point of the integer lattice other than 0. And you see this ellipsoid corresponds to the ball of radius 2r. And what we want is that the ball of radius r is going to pack. And so our volume is the volume of the ball of radius r, which of course is half the ellipsoid. Right? So the ball of radius r corresponds to ellipsoid divided by 2, rescaled by a factor of a half. So we want the volume of this rescaled ellipsoid to be at least the ratio we care about, this n-1, 2 to the 1 minus n, which I'm writing in a slightly different way for reasons that will now become fairly apparent. Namely, this is the same as saying that the volume of the ellipsoid itself, before scaling by a half, is at least 2 times n-1, because in n dimensions, if you scale the ellipsoid by a half, you scale the volume by 1 over 2 to the n. And actually, throughout the arguments, you can take the view that this 2 to the n that appears in the lower bounds, in a sense, always comes from this interaction between the ellipsoid, which is not containing lattice points, and the one that you actually pack, which is half as big. In a sense, that's where the 2 to the n always comes from. And so this kind of problem, I mean, of course, this is the result I'm trying to prove. When I started out, I didn't know that this was the result I'm trying to prove. But this sort of question, how big can you make an ellipsoid which contains no integer lattice point other than 0? This, in a sense, dispenses with the 2 to the n, and it's this number which is the thing that we're really trying to make large. Okay, so this was the sort of standard setup that everyone understood was the way to tackle sphere packing, to try and find nice lattice packings. And the story of this piece of work is that I was visiting a well-known maths department, and a number of theorists, well-known number of theorists, came up to me at tea time on a Friday afternoon and said, I've heard that you work in geometry. I was just a postdoc, but someone mentioned I worked in geometry. And he said, how about if we did some work together on sphere packing, maybe number theory and geometry together, we can do something on sphere packing. So I said, great. And he said, okay, well, why don't we both go away for the weekend and see if we can come up with any kind of crazy idea about how to think about sphere packing, and then meet again on Monday and share our ideas and see if there's anything we think might be worth pursuing. So off I went, and bright and early Saturday morning, I woke up, had my breakfast and shower and so on, and then sat down to come up with a crazy idea. And funnily enough, crazy idea appeared really rather quickly, for quite a good reason, namely that a little bit earlier, a year or so before then, I'd worked on a problem called the Planck Problem, and actually proved this result, that if you have unit vectors in a normed space and some positive numbers, whose sum is not too big, then you can find a linear functional on the normed space which is large at each of these unit vectors. So the value at each ui is at least alpha I, this positive number. Now, you can see that this theorem generalizes the Hahn-Banach theorem, or at least one of the most well-known consequences of the Hahn-Banach theorem, namely that each point of the unit ball of a normed space has a supporting hyperplane. So when there's only one of these vectors, you would get that standard Hahn-Banach theorem. But the theorem also gives you a sharp version of the uniform boundedness principle, a sharp quantitative version of the uniform boundedness or Banach-Steinhaus theorem. So it says that if you have somehow big vectors, you can find a functional where they're big, and that's really what happens in the uniform boundedness principle. So this was the thing I'd been working on, which gave me the crazy idea that I'm going to describe. But I should explain that the Hilbert space case of this was proved a long time earlier, in 52, so 40 years earlier, by Torger Bung, a Danish mathematician. And actually what we should want in this particular case, for this particular sphere packing problem, is the Hilbert space case. So in fact, for the rest of the talk, I shall be referring to Bung's theorem, or Bung's lemma, it's sometimes called. The only reason I mentioned that the generalization to other norm spaces is because it was actually the fact that I'd worked on this that led me to come up with this really crazy idea. I mean, it was a genuinely crazy idea. I'll try and explain to you why it is so crazy, because of course it's sort of important to understand that in a way. Okay, now before I do that, let me just remark that the result I put up on the previous page is optimal in the general case, if you look at L infinity and you're trying to find a functional in L1. But in the Hilbert space case, the result as stated isn't optimal, and it was an old conjecture of Fierstadt that it could be improved. He conjectured that the extremal cases are arranged sort of like the spokes of a wheel. And this conjecture was proved recently, a few years ago, by Zhang and Polyansky. And then about a year later, a very different proof was given by my student Ortega Moreno. So this has actually been solved. And if you're interested in this sort of topic, I recommend both of these papers. They're both absolutely gorgeous papers. The arguments are very, very beautiful. And so well worth having a look at. Okay, so what was the crazy idea? Well, let's take a ball of very big radius r. So capital R, not like little r, which is the balls you're packing. Capital R, very, very big. And let's look at all the lattice points inside it, all these integer lattice points inside the ball. Now, suppose we can find a unit vector whose inner product with all these lattice points in here is at least some number theta. Then what that tells us is that there is a slab of width 2 theta, so theta either side of the origin, which sort of can be woven among the lattice points. It doesn't contain any lattice points in its interior, so you can sort of just slip it in there, this slab. Of course, it contains 0, but it doesn't contain any non-zero lattice point. So you can fit this slab in there. And then, of course, that slab will contain an ellipsoid, and you can write down what its semi-axes are. In n-1 directions, the semi-axis is capital R. It's just bounded by the ball. And then in this one direction, in this direction phi, the semi-axis is theta. Right? That's the amount you're moving away from the origin before you get to the edge of the slab, because the inner product with this unit vector is at least theta for each of these lattice points. So in other words, this theorem of Bong, so this is the statement, but in the case of Hilbert space, I'll put it up on the next slide, automatically somehow constructs you an ellipsoid which misses all these lattice points, and that's what you want to do in order to pack balls. But it's kind of a crazy idea, because this theorem of Bong has absolutely no connection to sphere packing. It wasn't designed in any sense to do with sphere packing. It's a statement just about inner products, and there's absolutely no reason it should give you a nice bound in sphere packing. It might not give you any bound that you can easily compute, and even if you could compute it, it might be that as r goes to infinity, that the bound gives you nothing at all, and that if you pick a particular value of r, you can't really do the calculation. I mean, it really looks kind of wild, and there's really no reason why such a theorem should give you anything nice in the case of sphere packing. Well, let's see what it does give. So here is the theorem, 51, sorry, not 52, 51. You've got unit vectors in Rn, alpha I are positive numbers, add up to 1. Then there is a unit vector whose inner product with each of these unit vectors is at least the corresponding alpha. So this is the statement of the theorem in the Hilbert space case. It's due to Bong. Now, we want the inner product against each integer lattice point to be big. And of course, those lattice points are not unit vectors. So we have to rescale them. So we look at all the non-zero lattice points Z, and then we rescale each one by its length to get a unit vector. And we want the inner product with each of those to be at least theta, but that means that the inner product with each of the lattice points to be at least theta, but that means the inner product with this unit vector is theta over the length of the vector. So these will be our alphas, one for each lattice point, theta over the length of z. And then we know that there will be a unit vector which achieves this particular value of theta. You see, we're trying to make theta as big as possible to get the biggest ellipsoid here. We know that we will be able to achieve it if the sum of all these weights is 1, or is at most 1. Okay, so theta over these things, we add up over all the non-zero lattice points whose length is at most capital R. And if that quantity is at most 1, it's equal to 1, then that theta is an allowable thing to put in here, and that means that we'll get an ellipsoid of that size, theta times r to the n minus 1 times the volume of the Euclidean ball, because this ellipsoid is stretched by these, is Euclidean ball, but stretched by these semi-axes. Okay, so our aim is to calculate or estimate this quantity here, and if you just pick a particular value of r, it's not really very easy to estimate how big this is. But we can play a kind of a trick, kind of a standard trick, actually, not really all that surprising, in fact, to estimate this thing. The point is that when capital R is very large, we're looking at lots and lots and lots of lattice points, and adding up something over lots and lots of lattice points is going to be a bit like taking an integral. So let's see how we do this. So this is what we're trying to achieve. We're trying to cook up theta so as to achieve this. How do we estimate the sum? Well, we make a substitution. We say, suppose z is r times w. So I pull out the r from length of z on the bottom there. And now you see the sum runs over all non-zero points, not in the ball of radius r, but in the ball of radius 1, because I've scaled by r. And no longer integer points, but points belonging to a grid with a very fine mesh. So I've rescaled by a factor of r, and so the mesh size is no longer 1 for the integer points, but it's now 1 over r for these rescaled points. So here I've drawn sort of the same picture again, except this time it's now the ball of radius 1. So you interpret it differently, even though it looks similar to the previous picture. It's actually telling you something very different. This is now the ball of radius 1. And these points are no longer integer points. These points are now very close together. Their distance is 1 over r between neighboring points. And so you have this very fine mesh laid over the ball of radius 1. And then this quantity here, as r goes to infinity, this converges to an integral. This is the Riemann sum of a certain function, namely this 1 over the length of whatever it is, the point we're talking about. It's that Riemann sum, and you see we've multiplied each value by 1 over r to the n, because that's the volume of the little cube attached to that point. If you like, you can think of it as being sitting around the point, 1 over r to the n. The side length is 1 over r, so the volume is 1 over r to the n. So this is kind of a Riemann sum. I mean, strictly speaking, I'm being a bit naughty because I have to exclude 0, where this thing doesn't make sense. And of course, you're not really allowed to take Riemann integrals of unbounded functions, but you understand what I mean. It's like a Riemann sum. You can always exclude some tiny sphere in the middle and do the calculation that way. So it converges to this integral. Now, when the dimension is 1, when n is 1, you're integrating something like 1 over x, and you know that diverges logarithmically. So when n is 1, you get infinity here, as the formula indicates. But when n is larger than 1, the integral makes perfect sense. So in higher dimensions, the volume of a little ball near the origin is so small that it compensates for the largeness of the function, and so the integral converges perfectly well at 0. And you get n over n minus 1 times the volume of the ball of radius 1, the ball that's actually illustrated here. Right, so we know essentially how big this is when r is very large. That's good. I've written it down again there. And now remember, our aim was to choose theta so that this quantity here is at most 1. It's 1 over z, but the z is r times w. I pulled out the r. So I want to cook up my theta so that this quantity is at most 1. And that's the same as theta times r to the n minus 1 times this thing. You see, I've got 1 over r instead of 1 over r to the n, and so it's theta times r to the n minus 1 times this thing, which is that. And so I know that the expression I want to be at most 1 is essentially this. And now you see, without really having to worry about what theta actually is, if you look at this theta r to the n minus 1 volume of the ball, that is the volume of the ellipsoid that fits inside the slab. You remember I explained that the ellipsoid has these semi-axes, theta, n minus 1 axes of length r, and so its volume is the product of all those and the volume of the ball of radius 1. So you see these factors here, theta r to the n minus 1 and volume of b1, just gives you the volume of the ellipsoid. And so whatever theta we want to cook up, what we actually end up with is this, that the volume of the ellipsoid is n minus 1 over n. Well, we were trying to find an ellipsoid, if you remember, whose volume was at least 2 times n minus 1, an ellipsoid containing no lattice points, integer lattice points, whose volume was 2 n minus 1 rather than this thing here. So we appear to be wrong by a factor of 2n. Actually, this argument I went through, I could have modified it slightly to get twice as big, an answer twice as big or a result twice as big, because you see, for each point here, it's got an opposite point, and if I exclude one of those from my slab, then I automatically exclude the other because the slab is symmetric. Perhaps the previous picture is better. So this point here, if I exclude that, then the opposite point is automatically excluded as well because the slab is symmetric. So I could start off by breaking partitioning the integer lattice points inside this ball into 2 sets, so that each pair of opposite points has one point in one of the sets and one in the other, and then just sum over, take this sum over for one of the sets, so half the lattice points, and that'll give me half as big a value, and that'll mean that I can take theta to be twice as big. So I could actually get 2n minus 1 over n. So it's not quite as bad as we thought, but still it's wrong by a factor of n. And actually, this would give me essentially Minkowski's bound if I got this extra factor of 2. It's not exactly, but roughly speaking. Okay, so we're wrong by a factor of n. Now, this was the calculation I did over that weekend, and in the end, actually, the person who'd spoken to me said that when I met him on Monday, he said unfortunately something had come up and he wasn't able to work on this. But I said, well, don't worry, I've had this crazy idea. I'll just think about it and see what happens. And you might say, well, you know, I got this thing, and I might be a bit disheartened. But in point of fact, of course, I was not. And the reason is that, as I say, this was a really crazy idea. There was no reason it should give anything nice at all. It might have given something wrong by a factor of 2 to the n, or might not have been able to calculate. It might have, you know, as r went to infinity, it might have given me 0. Who knows? I mean, on the face of it, when you first look at the statement that you're going to use, this lemma of Bong, there's really no reason it should give you any nice result on sphere packing at all. And yet it almost gave us something good. I mean, it gave us at least what Minkowski got, and that's really very striking. And when something like that happens, you think to yourself, right, I'm going to keep trying because, you know, I've been given a remarkable gift here, and so I shouldn't, you know, ignore it. I shouldn't sort of look the gift horse in the mouth. Instead, I should say, okay, can I actually get something a little more out of it? And so you carry on working. Okay, so we've got to improve this by a factor of n. How are we going to do it? Well, in the end, I'm going to show you how to prove the result. And usually in the past, when I've given this talk, and I've given a talk based on this topic, I've given it quite a few times, and I've always just gone straight for the answer. I've just given the sort of a slick proof. I haven't included all this stuff about this particular, about the slab and all the rest. I've gone for the sort of the end result. And in this particular case, I thought that because I was speaking to a summer school, it might be better to do it the way I'm doing it here, and start off with the basic idea, and then show you a little bit what went on behind the scenes, leading up to the eventual result, which actually improved upon the existing bounds, Davenport and Rogers in particular. Rather than just give you this very slick, very quick proof, I would actually take you behind the scenes and show you what happened, what led, a little bit of what happened. Of course, I can't show you everything. It took several months, and there was lots and lots of full starts and calculations and things like that. But at least this problem lends itself a little bit to describing several stages at which the result improved. So the first stage was this: look for a slab. That's what Bong's theorem tells you. Bong's theorem tells you you've got big inner products. Big inner products means you're outside a slab. The obvious thing to do. It doesn't beat the existing results, but it at least gets you closer than it might. I mean, it gets you to Minkowski, which is already a huge step from nothing. Okay, so the rest of the talk, I'm going to show how I managed to get the extra n, and it happened in 2 steps. The first step is something which we use quite often in mathematical research. So I invoked the theorem of Bong in order to prove the previous bound, or get the previous bound. And the theorem of Bong was stated in a particular way, but very often the proof of a theorem actually gives you more than the theorem that people sort of wanted. I mean, of course, when you prove something, if it is a proof, it will give you what you want, but there's a good chance it'll give you more because the proof has somehow been arranged to work, and then it gives you something which has to be at least as strong as you want, and there's a good chance it's going to be stronger because why should the proof give you exactly what you want and nothing more? And so after a couple of weeks of being very pleased about this, but wanting to do better, I remembered that the proof of Bong's theorem actually tells you something much, much more. It says that if you have unit vectors and positive numbers, as before, then there is a vector of this form. So what is it? It's a linear combination of the unit vectors with these weights, these positive numbers, together with a choice of signs. So plus or minus SIGN sign, each one being plus or minus. There is a vector of this form which satisfies the bound you want, the inequality you want for each of the inner products. Now, in the case that you're told that these weights add up to 1, which was the original hypothesis of Bong's theorem, then by the triangle inequality, the norm of this phi is at most 1, because you've got the signs and you've got the alphas and you've got unit vectors. But of course, this is only going to be sharp, this is only going to be a good estimate if these ui's more or less point in the same direction. And we're applying this theorem to all these scaled integer lattice points. So you take the integer lattice points and you form unit vectors by scaling them by their lengths. And those are the things that we're going to feed into this theorem of Bong. And of course, these lattice points don't all point in the same direction. In other words, quite the opposite. They point in all different directions. I mean, practically almost any direction you want, there's going to be a lattice point in it, particularly when R is very, very large. So we're very, very far from the case of equality in this application of Bong's proof, as it were. So it may very well be that we can get a better estimate for the length of this thing using the fact that these are indeed the rescaled lattice points and therefore not at all in the same direction. Okay, so how does that work? Well, we're going to choose theta so that this phi will have length 1. So let's actually write down length of phi is 1. That's what this says. And now let's replace one of these appearances of phi by the sum that we want. So here I've got the unit vectors, I've got the weights, 1 over length of z, and I've got these signs, SIGN, and then I've got this extra factor of 2, which comes from the fact that I could have used half the lattice points instead of all of them. So I'm going to estimate the length of phi by testing phi against phi. I'm going to estimate the length of this thing by testing it against a unit vector, which happens to be itself, of course, but it doesn't really matter. I'm testing it against this unit vector. So I now take the inner product through the sum, no problem. And now I apply the triangle inequality here, and it says that because this is a choice of sign, I can replace that times the inner product with the absolute value. So I get this now as my estimate. And notice that this is similar to what I had before, but instead of 1 over the length of z, I've got an extra factor of this inner product over the length of z. And of course, that inner product over length of z is definitely less than 1. This is an inner product with a unit vector. And in most directions, of course, z will have a small inner product with this particular unit vector phi, whatever it may be. I mean, we happen to know that it's this, but who cares? It's just a unit vector. So most lattice points will have a much smaller inner product with phi than the size of the vector itself. So this quantity should be much less than the previous weight that we added up this thing here. And that's going to give us an extra factor. So we go through the whole argument again with these Riemann sums and convert this to an integral, and we change the r to the n to r n minus 1 and so on. And now we have this integral instead of the integral 1 over w. And it turns out that this gives you approximately the same thing we had before, but with an extra factor here, square root of 2 over pi n. So what we had before was this c to the r, theta times r to the n minus 1 times the volume, this n over n minus 1, and then there's also this factor of 2, which I've sort of stuck in by my choosing only half the lattice points. But this time, because of this inner product over the length of w, I've got this extra factor, which is good because it's small. It's a square root of something over n. Now we're trying to get an extra factor of n, and this only gives us a factor of root n, but at least we're kind of halfway there. So this has won us a fair bit, but let's try and understand why we get a factor of something like 1 over root n by doing this. And the answer is not too difficult. So my question is, why is this integral essentially the same as the original one, but with root 2 over pi n in front of it? So my question is, why is it that a typical vector, typical in the sense of, as it were, randomly chosen from a ball, should have inner product with phi, which is approximately 1 over root n times its length? So we replace the length by the inner product over the length squared, so the extra ratio is the inner product divided by the length. Why should that be about 1 over root n? The answer is kind of simple. If we're looking at a typical vector, it doesn't really matter which direction phi is pointing. They're all the same by symmetry. So let's assume it's the standard basis vector direction, the first coordinate direction. So this inner product is just the first coordinate of w. Why should that be about 1 over root n times the length of w? Well, because the length of w squared is the sum of the squares of the coordinates, and so there are n of them, and so each one, assuming they're roughly equal, which presumably they tend to be, will be 1 over root n times the length. Now this was something, of course, I was very well aware of from working in geometry. It's a kind of a standard thing that you observe all the time in geometry, and so I knew as soon as I saw this inner product that I was going to get this extra factor of 1 over root n, and indeed that was really what, of course, enabled me to see from this point that I was going to get something by taking advantage of the fact that these ui's don't all point in the same direction. So this is just a sort of a trick for actually doing the calculation, but you see that the idea behind it is that if you've got things pointing in all directions, then the extent to which you won't satisfy the triangle inequality will be this factor 1 over root n, because only the direction of phi really matters. So the length here depends only on the components of these vectors in whatever direction they end up, the sum ends up pointing in, and that would be 1 over root n times the length. So you can improve the triangle inequality by root n because these things point in all different directions, and only one direction matters for the length of the sum. So that explains the kind of the argument here. Okay, so that wins us a factor of root n. How do we get the remaining root n? Now, I mentioned that the crazy idea took really very little time at all. I mean, I sat down on a Saturday, and by Saturday lunchtime, I got the idea, and so the crucial crazy idea, use Bonk's theorem, took a very short time, even though it was the main idea. This second idea, use the actual proof of Bonk's theorem, that took about 2 weeks, and it's a good idea. It's the kind of thing that happens in maths. Sometimes we want to use the proof rather than the actual result, because the proof gives us more. And then the final step, this final root n, took another 6 weeks, so even longer, despite the fact that it was kind of obvious. Once I sort of thought of it, it was kind of the most trivial part of the whole argument. And this is also something which one sometimes has to get used to in research, that weirdly, the easy bits sometimes take much longer than the difficult bits. The difficult bit sort of pops into your head. That's the achievement. That's the research. And then the easy bits are how you make the thing work. And often it can be quite hard to make the thing work, and you have to sort of think. Of course, without the difficult bit, the idea, you'd have nothing to work on. But once you've got the idea, somehow, the filling in all the stuff you need may take quite a lot of effort. It doesn't just pop into your head. You have to sort of dig it out. And that's why it takes a long time, even though actually it's much, much less important. So this is one of the features of research, which is kind of tricky to learn, really, or can be tricky to learn. But it's if you find it happening, don't despair. Don't think there's something wrong. It's quite natural. Okay, so our problem is to weave a thin ellipsoid among the integer lattice points, and the ones of size at most R. That's what we're doing with this picture. And I said, well, let's do it by taking a slab. And the reason I chose a slab, of course, is that a slab is what inner products tell you about, right? So that's why I knew I could get a slab and then inside an ellipsoid. But suppose we say, well, let's forget the slab and let's just say, what do we have to do to weave an ellipsoid? Well, we're going to have this direction, this phi, or whatever it may be. And then, of course, all the other directions, the ellipsoid is going to have radius r. And that means that the equation of the ellipsoid, or the inequality that determines the interior of the ellipsoid, is this one, right? So if y is perpendicular to some vector x, then this just says the length of y is at most r. So in most directions, so our x will be in this direction, phi, if you like, but it's not going to be a unit vector. It's going to be something like that. And so perpendicular to x, the length is just capital R. But in the direction x, we get much, much stronger control of how this y varies. So we get a huge additional term if y is in the direction of x. This will be the equation, or the inequality determining the ellipsoid. And our aim is that there should be no integer lattice points, non-zero integer lattice points in the interior. In other words, that for all integer lattice points, this quantity here is at least r squared. That's what we want. And now you say to yourself, well, of course, I didn't realize this to begin with, but actually, this is a statement about the inner product of the lattice point with x. It says that the inner product is at least this thing, the square root of r squared minus length of z squared. And the point is that when we apply Bong's lemma, we're allowed to choose what these alphas are, these numbers that we beat with our inner products. And of course, this may look like a very weird number. It's depending on this lattice point, but that's fine. We're allowed to have these weights depending on the lattice point. And actually, there's no reason why we shouldn't pick this. It happens that this is what you actually need to control an ellipsoid. So of course, once you write this down, it's obvious. And yet, geometrically, it was hard to think of, because you think big inner product says you're outside a slab. It doesn't. You don't think it says you're outside an ellipsoid, but of course it does. It just simply does, as long as you interpret the word big in the right way. So this is what we want to achieve. And so now you see we've got to find a vector x whose inner product with these unit vectors, the rescaled lattice points, is at least this weight. So I've rescaled by dividing by the length of z, so I get this quantity here. This will be my alpha sub z, my alpha corresponding to each lattice point. And so, of course, I'm going to put that into Bong's argument, if you like, the sum involving these signs. So here is my unit vector, here is my weight, here is my choice of sign, here's the extra factor of a half. And this will be my x. And then based on that x, of course, I'm going to calculate the volume of this ellipsoid, and then we'll be happy. So how big is x? Well, we use the same Riemann sum idea. We get an integral. And then I haven't put in all the details again this time. You can go through and check it if you want. But the key point is that we have this same thing here, the same factor in a product over length. But now we've got this factor, which is supposed to win us the other root n. So this factor wins us root 2 over pi n, and this factor is supposed to win us another root n, and then give us the result we actually want. So as before, let me try to explain to you why it's reasonable or appropriate to expect that this factor will win you root n. Okay, so I gave a kind of heuristic argument as to why this factor should win you root n. Now let's see why this factor should win you root n. Well, as this w, the point that we're looking at, this point in the unit ball w, moves out to the boundary towards the surface of the ball, this factor will decrease to 0. So when the length of w is 1, this factor is 0. So what we care about here is how likely is it that w is near the surface of the ball, and the answer is very likely. So in n dimensions, most of the mass of the ball lies near its surface, and actually we already saw that when we did the very first integral. So when we did this integral here, we saw that the average of the reciprocal of the radius is just n over n minus 1. So if we divide by the volume of the ball, we get n over n minus 1, and that's the average value of this, meaning that a typical point has length n minus 1 over n. Okay. And that, of course, is exactly saying that a typical point is near the surface of the ball. Its length is 1 minus 1 over n. Now we can expand on that a little bit and sort of understand it a little bit more geometrically in the following way. Suppose you shrink the ball by this factor 1 minus some number t over n. Then the volume shrinks by that to the power n in n dimensions, and that quantity is essentially e to the minus t. So if t is like 5, you shrink the ball by a factor 1 minus 5 over n, the volume's essentially disappeared. E to the minus 5 is tiny. So almost all the mass will lie within, let's say, 5 over n of the surface, or 3 over n, and so on. Basically, a distance something over n from the surface. So almost all of the mass lies in a shell of thickness about 1 over n, which of course in n dimensions is rather small. So the typical point has length 1 minus 1 over n, and that means that when you evaluate this quantity, it comes out to be about 1 over root n. So this thing on the bottom will be 1 minus 2 over n, its reciprocal 1 plus 2 over n. So this is, let's say, root 2 over n roughly. And that's how we win the extra root n. Now, you're sophisticated people, and so you look at this integral and you say, okay, this bit wins us root 2 over pi n, and this bit wins us root 2 over n, and so we get some sort of factor of constant over n coming out, which is what we want. We wanted to win a factor of n, and you understand that it's not going to give us exactly this bound. This bound is obviously something where I've said asymptotically it works out to be this, or maybe it's 1.01 times this, and I just ignore the 1.01 since it's not terribly significant, and so on. As a sophisticated mathematician, you understand that it's not going to be exactly this bound, and you'd be wrong. So in every dimension, you can do this integral exactly, and it comes out to be exactly 1 over n minus 1, which gives us exactly this bound when we apply all the argument we've had before. So somehow, not only were we given a remarkable gift that Bong's theorem actually gives something in sphere packing, in the end, we got an even nicer, well, perhaps not quite as nice a gift, but an even more shiny gift, that everything just works out somehow exactly right, and we get exactly this bound, which was at the time a new bound. Okay, now when I was giving the lecture in the summer school, it turned out that the sound was very distorted, so I've re-recorded it, and that's what you're hearing now. And I was asked a number of questions. I won't go through all of them, but one of them was quite memorable, and I think I would like to just mention it. So Mircea himself actually asked, why did you stop here? Why didn't you go on and try and get more improvements? Okay, you'd taken several steps. You got the first bound, which was no good, and then you got an extra root n, and then finally another root n, and it worked out that you managed to just beat the existing bounds. Why didn't you carry on? And of course, one argument is, well, I mean, I couldn't see anything that worked, so I stopped because I had to. But actually, it's not quite true, and I think it's kind of important to understand that. You see, there's something kind of right about the way this works. Once you get to this point, you've been given a very generous gift, and it would almost be ungrateful to say, "Oh, I want more." It would be greedy. And I'm sort of being serious here. Of course, I'm not really. I'm joking, but I'm being kind of serious that one shouldn't be greedy. One should know when to stop, because one should understand that somehow the argument, as it now stands, with this choice of the weights and this integral to evaluate, somehow it is the correct thing to do if you're using Bong's lemma. It's not necessarily the correct thing to do for sphere packing. Indeed, it can be beaten, but if you're using Bong's lemma, it is kind of the right thing to do. And somehow, when something feels right, it's appropriate to stop, I think. And because otherwise, you could spend 2 years trying to improve it, not get any result, and think, "Well, I wasted 2 years." You have to accept gifts graciously in mathematics. And as I say, I'm sort of joking here, but not entirely. In that this is a summer school, I want to kind of convey some more information beyond a cute argument. Okay, that's the end. And once again, thank you to the organisers of the summer school. I think it was a very good idea.